So, last time we discussed the case of vibrations of a crystal lattice, in particular an infinite one dimensional lattice of identical atoms, and considered what would be the normal modes of and the frequencies of these modes of vibration. We got the basic what are known as the dispersion relation, which has the form omega equals omega max sin q a by 2, where omega max, it is a maximum angular frequency, which is root of 4f by m. Here we just to recall, q is the wave vector of the periodic wave, the acoustic wave which propagates, and then or wave number. This is a one dimensional infinite one dimensional lattice vibrations of so F is the force constant between adjacent atoms which are identical and each of mass m, identical atoms which are vibrating, and this is taken to be a harmonic, simple harmonic vibrations. A is a repeat distance or periodicity along the line of atoms. So, that for q in the q tending to 0, which means the wavelength is long wavelength, then we know that this dispersion relation becomes, because sin q a by 2 in the limit q tending to 0 is q a by 2. So, this is omega max into a by 2 times q. So, a constant omega q relationship is a linear relationship, very much like the standard sound waves. So, in the long wavelength limit, the dispersion relationship gives you a linear dispersion relationship, which is shown in the figure. So, where you have the omega as a function of q. So, it goes like this in close to this, but beyond for larger values of the wave vector, this changes, this deviates and is given by this dispersion relationship, a sinusoidal relationship. So, this is the basic content of these one dimensional lattice vibrations, and these are the excitations, the quantized excitations of energy h cross v q, where v is the velocity of sound wave, sound speed, speed of sound, gives you the, this gives you the energy quantum of energy of these phonons, which are the quantized excitations of these lattice vibrations of this crystal lattice. Of course, we have made an approximation, we have made the harmonic approximation, we have also taken this line to be a lattice to be an infinite lattice and so on. So, we would like to consider real situations where these assumptions are slowly removed, so that we have a finite one dimensional lattice of n plus 1 atoms, that is the 0th atom and then 1 and so on, then you have n. So, counting from 0 to n, you have n plus 1 atoms in this, as shown in figure, and where n is finite. So, we are considering this again, the model is the same, we are considering restoring forces which are simple harmonic, and the two atoms at the end, the 0th atom and n atom at the end are at rest, they are held at held bound. So, there are only n minus 1 mobile atoms. Okay. And now, because this is a bounded chain which goes, which is has the boundaries at the ends. So, it is the solution is taken not as travelling waves, but as a superposition of two travelling waves. In general. So, we take for example, x n of t, the displacement of the nth atom is taken to be a e to the power I omega t plus q n a plus b e to the power I omega t minus q n a, where n is the nth atom. Now, that is a progressive wave which is going from left to right, and this is a wave like solution which moves from right to left. So, the general solution is taken to be a superposition of these two, so that you get kind of standing waves in the system, because the ends are held fixed. So, the boundary conditions are x of t for n equal to 0 and n equal to n is 0. There is no net displacement for any one of them. So, x 0 t and is 0 and x n of t is also 0. The atoms at the end are held fixed. So, if you consider such a situation, then in general this superposition with this boundary condition, we get A equal to minus B, as you can readily verify. Therefore, this becomes and that is nothing but 2 I A e to the power minus I omega t sin Q N A. Because of this boundary condition. So that now since e to the power minus I omega t is nothing but cos omega t minus I sin omega t, therefore, the real part of this solution real is just, if you take this, this will become I times this. So, this will be 2a sin omega t sin n q a, that will be the real part. Now, using this as the solution, the equations of motion of course are the same. Therefore, applying this to the equation of motion, we get the same dispersion relationship as for the infinite chain. So, now that is the same. So, we arrive at the identical. I do not want to prove this, I just it can be readily verified with this solution and with the equation of motion which we considered already in the last lecture. Now, we apply the second boundary condition, namely x n of t also is 0. So, the nth atom is also at rest. So, when I substitute this, this becomes 2a sin omega t sin n q a, and that is equal to 0, giving immediately q n q a equal to m pi, where m is an integer. So, the allowed modes corresponding to different q values are restricted by this condition, that is the second boundary condition. So, we have finally we have q equal to m pi by n a, which we can write. N a is the total length of the chain, there are n atoms each a apart. So, this is nothing but m pi by L, where L is the length of the chain of atoms. So, we have this, and the modes of vibration, the density of states can all be found using the same conditions as we did earlier, and we get the density of modes d of q dq, which will be L by pi times dq. L by pi is the number of modes per unit q value, length in q space. So, if you take an interval dq around the q value, it is L by pi dq. So, this is the density of states. Phonon density of states. Using this, we can again calculate, because we know the internal energy, for example, the specific heat. How does this get modified? Because why have we done that? What have we done here? We have departed from the Debye assumption of a continuous medium, a continuum, and replaced it by a discrete finite one dimensional lattice of atoms, taking into account the periodicity and the discreteness of such a lattice. So, again we find h cross omega by e to the power h cross omega by kBT minus 1. This is the average energy which we discussed already in connection with the d by solid and then multiply by L by pi dq integrate from 0 to pi by a, and that would give me, this is omega q, where omega q is related to the dispersion by this, therefore replacing that. So, that would be the corresponding expression, and the specific heat is got by differentiating. The specific heat is just du by dt as before. So, this is the modification to the Debye theory, which is brought about by removing the model of a continuum and replacing it with a discrete one dimensional. The extension to 3 dimensions is straightforward. I will not go through that now. Okay, but let us consider, while we are talking about the lattice vibrations which give rise to phonons with different modes, we will extend this model that we have just discussed to the case of an infinite one dimensional lattice, but of 2 different types of atoms. It is called a diatomic lattice, not a monatomic lattice. Why is this important? The reason for the importance comes from the fact that many solids are diatomic nature, many standard common solids like sodium chloride, for example. So, you have an infinite lattice, of course a 3 dimensional lattice, but we will consider for simplicity an infinite one dimensional chain consisting of sodium ions and negative chlorine ions. So, they are of different masses. So, they are arranged alternatively. So, you have a lattice of Na plus, Cl minus, again Na plus, Cl minus, like that. So, we have again considered an infinite lattice, the spacing is the same. So, let us consider the 2nth atom, say this is the 2nth atom. So, you have many such. So, you have its neighbor 2n minus 1 and another neighbor, next neighbor, we consider only next neighbor interactions. So, the displacement is taken of the 2nth atom is taken as x2n, and the corresponding displacement of this atom is x2n minus 1 and this is x2n plus 1. Now, this is an atom of mass m, while this is another atom, these two are atoms of mass small m. So, obviously, the equations of motion are going to be different from that for the monatomic lattice. So, let me write the equation of motion. For example, for the atom of mass m, that will be m d square x 2n by dt square. This is the mass times acceleration is given by minus f times x 2n minus x 2n minus 1 minus f x 2n minus x 2n plus 1. And a similar equation, there are two equations now, one for the mass capital M and the other for the small m. So, this will be minus f times x 2n minus 1 minus x 2n minus 2, that would be the neighbor here on this side, and minus f times x 2n minus 1 minus x 2n. So, these are the equations of motion in the harmonic approximation. These are the equations of motion, which we have to solve using an identical procedure. So, we have, since it is an infinite lattice, we can assume travelling waves solutions. So, we assume x 2n equals a e to the power minus I omega t plus q into 2n a, and x 2n plus 1, for example, is not necessarily b, it will be this, it will not be the same, omega t plus q into 2n minus 1 a. So, a and b are the amplitudes of the vibration of the atoms of mass capital M and small m respectively. Substituting this in the equation of motion and doing the differentiation etc., and solving them, we arrive at a determinantal solution, which is the solution for the resulting simultaneous equations. So, this times a plus 2f b cos q a equals 0, and similarly m omega square minus 2f b plus 2f a cos q a equals 0. These are the simultaneous equations which result from this. So, solution of this requires the determinant of the coefficients to vanish for a non-trivial solution. So, setting this determinant equal to 0 and solving the resulting quadratic equation is a 2 by 2 determinant, which has the form so that would be the determinantal solution. So, solving this resulting quadratic equation, we get omega square equals f times 1 by m plus 1 by m plus or minus f times 1 by m plus 1 by m square minus 4 sin square q a by m times m. So, that would be to the power half. So, since we are looking for real solutions for the frequencies, we take only the plus sign here and then write the solutions, and so we will have two solutions corresponding to the plus and minus sign. So, you will have omega 1 and omega 2. So, we will have dispersion curves which will have two branches corresponding to omega 1 and omega 2, or omega plus and omega minus. So, this can be plotted just like in the case of the monatomic solid. So, So, this gives the modes of vibration, normal modes of vibration of a diatomic lattice, an infinite one dimensional diatomic lattice. So, that is the essential difference between these two, this case and the previous case. So, you have the acoustic and optic branches, and these are the allowed phonon modes which must be used in calculating the characteristics of such a lattice, for example sodium chloride and similarly other alkali halides. So, having discussed the properties of phonon modes, the allowed phonon modes for simple models of the solids, we can try to see what it means for the thermal properties that we discussed already. We already talked about specific heat to some extent, but let us now go back to thermal conductivity. So, in the case of thermal conductivity, we have already discussed the thermal conductivity of a metallic solid, and the thermal conductivity arises mainly from the conduction by the electrons considered as a gas, and we use the kinetic theory expression for the conductivity, namely K equals 1/3 C V L. Now, here C, this is the thermal conductivity, so V is the C is the specific heat or heat capacity, V is the speed and L is the mean free path. This is the expression that we have already used in connection with the electron gas and how the thermal conductivity contribution due to that. We have already seen that the Wiedemann-Franz law in the case of a metal, we have already considered how you have the so called the theoretical description leads to the Wiedemann-Franz law, namely K by sigma T equals constant, where K is the thermal conductivity and sigma is the electrical conductivity and T is the absolute temperature. So, we have seen this for metals. Now, we are going to consider what happens when the thermal conduction takes place in an insulator. In an insulator there are no electrons, there are no conduction electrons. So, if you have an insulating solid like a plastic or a ceramic or any such, so there are no conduction electrons. So, thermal conduction cannot take place through the electrons. So, the thermal conduction mechanism is via the phonons. So, the carriers of heat in insulators are the phonons and their exchange of energy and momentum between the phonons, namely the phonon-phonon collisions. They are the ones which give rise to thermal conduction in insulators. So, this is the reason why we consider the nature of the lattice vibrations. So, you have certain equilibrium distribution of phonons at any finite temperature T, and when there is a temperature gradient in the material, the phonon distribution will be disturbed. Phonon-phonon collisions will occur and this will tend to restore the equilibrium distribution. Now, this restoration will take place with a characteristic relaxation time. So, the rate of this restoring process is what determines the thermal resistance of the material. In a poor thermal conductor, the rate at which this restoration of equilibrium takes place is very slow. So, basically this is entirely due to phonon interaction. So, the interaction is described by equations which conserve energy omega 1 plus omega 2 equals omega 3. If you multiply them throughout by h cross, it becomes h cross omega 1 plus h cross omega 2 equal to h cross omega 3. This gives you the energies of two phonons of frequencies omega 1 and omega 2, resulting in a third phonon of frequency omega 3, angular frequency. There is also a conservation of momentum which is expressed by the equation of this kind, q1 plus q2 equal to q3. So, the momentum and the energy are conserved in such a process. So, this is known as a normal or N process. You can also have a situation where this is the same, but this becomes q3 plus g, where g is what we have seen already is a reciprocal lattice vector. Q is in reciprocal space, mind you. So, this such a where this is also allowed, and this is known as an clap process, known in short as a U process. So, both these processes are possible in phonon interactions. Both will contribute to the conductivity. So, this tells you a phonon of energy h cross omega 1 interacts with another phonon of energy h cross omega 2, resulting in the creation of a phonon of energy h cross omega 3. So, the total energy of the phonon system is conserved. This tells you the corresponding conservation of the momenta of the corresponding q1 and q2, h cross q1 and h cross q2 are the momenta of the interacting phonons, which result in the creation of a phonon with momentum h cross q3. So, if we take this equations, so you have change in the total momentum. Let us spend a little time on this clap. Clap is a German word which means folding up. So, let us just look at what this means. So, you have q space, let me just plot it in one dimensions. So, this is there and I have q1. So, this is the zone boundary, I have q1 and q2. And now I have q3, the result of these addition gives you say q3. Now, this takes it outside the zone boundary, and we have already talked about how we consider states within the zone boundary for all our discussions because of the periodicity. So, but this wave vector takes it, the combination of q1 and q2 takes it outside this. So, what do? We bring it back into this by adding a G, a reciprocal lattice. vector. So, this comes back into the first zone. In this case, of course, G will be in the opposite direction. Then this will be Q3 plus G, where G is in this direction. Therefore, this resultant vector will come back into the first zone. So, that is how this process takes place, and this means this reversal and bringing it back means that the scattering of the phonon can reverse its direction, its momentum. So, the thermal resistance can be appreciable because of this. So, these are the processes which can contribute to thermal resistance. In addition, you can also have boundaries like grain boundaries, and then there can be impurities. It is the Umklapp process which is dominant in thermal conduction due to phonons. So, each one gives a contribution, and the net conductivity is 1 by k Umklapp plus 1 by k boundary plus 1 by k impurity. Each one contributes, so that gives you the net k. So, this is the total conductivity. Conductivity is added in this way. It is the resistivities which are in series and the conductivities which are the reciprocals add this way. So, this is how we calculate the overall thermal conduction. Let us just spend a little time to talk about what is the temperature dependence. Now, if I consider this kinetic expression, kinetic theory, suppose we consider high temperatures. Thermal conductivity at high temperatures. We know that the specific heat is independent of temperature at high temperatures because of Dulong-Petit's law, we have already considered. So, the temperature dependence of the thermal conductivity is going to mainly depend on the thermal temperature dependence of the mean free path. So, that is what will give you the net overall thermal temperature dependence of the conductivity. Now, the mean free path is the average distance travelled by the phonons between successive collisions. Therefore, it will be the mean free path will become smaller if there are more number of phonons and there are more collisions. In other words, the mean free path for a given phonon is inversely proportional to the density of all the other phonons. So, in a given mode, we know that the number of phonons is given by 1 by e to the power h cross omega by kBT minus 1. So, this is the factor which will give you this. Now, this will be in the high temperature limit, you can check this will go as kBT by h cross omega. So, the mean free path which is inversely proportional to the number of phonons will go as L will go as T to the power minus 1 at high temperatures. So, that means that the Umklapp process, the mean free path will go also as Umklapp goes as T to the power minus 1 for temperatures T very large compared to theta d at a high temperature. If you have a pure solid which is well annealed, then impurity scattering can be neglected. There are not many impurities. We are considering a pure specimen. And if the crystal size is fairly large, then boundary effects can be neglected. So, we can forget about these. To a first approximation, when you have a pure large crystal. So, the thermal conductivity will essentially go by this. So, the conductivity will be proportional to the inverse of the absolute temperature, that is in the high temperatures. Now, let us go to the low temperature region. At low temperatures, the Umklapp process will occur only for Q of the order of half G. It should be half a reciprocal lattice vector, the interacting phonon wave vectors, because the resultant should be outside the first Brillouin zone. That for that to happen, this is the condition, and this wave vector corresponds to a phonon energy of half kb theta d. So, if we take such an energy, so what happens? The number of phonons which have this is going to go as exponential minus theta d by 2t. This is going to be the number of, because of the Boltzmann factor. So, the temperature dependence of the phonon mean free path L due to the Umklapp process must be proportional to exponential theta d by t, because the mean free path goes as the inverse of the number density. So, the correspondingly the thermal conductivity also for the U process will go as exponential theta d by 2t for t very small compared to theta d. This means as t tends to 0, this tends to infinity. But the total thermal conductivity will not go to infinity, because it is limited by contributions from the boundary and impurity scattering. At low temperatures, the boundary scattering will dominate. For a pure crystal, the mean free path of phonons is nearly equal to the dimension of the crystal, because the mean free path becomes, if the crystal is pure, the phonons have no impurities or defects, and therefore, the mean free path is nearly equal to the entire dimension of the crystal. It becomes very large. So, it will become practically independent of the temperature. So, the temperature dependence of K will be mainly due to the temperature dependence of the specific heat, because this becomes temperature independent, and this goes at low temperatures as T cube for T less than theta d. This is the d by specific heat behavior. So, we have at these temperatures the K will go as T cube. So, therefore, if you consider everything together, the thermal conductivity of an insulator increases with increasing temperature, starting from very low temperatures, being proportional to the cube of the absolute temperature, and later Umklapp processes take over, and then the thermal conductivity decreases exponentially. If you change the temperature further, if you increase the temperature further, it varies as t to the power minus 1. So, the overall temperature dependence is shown in figure 5. So, it goes somewhat like this. you have a peak. So, this is the temperature dependence or the thermal conductivity of an insulator. So, such a variation has been experimentally observed.